In this lecture of module 2, we would be discussing combinational circuit design considering variations. We had discussed inverter and now we will discuss NAND gate and also other several sources of variation. In the previous lecture, we have discussed inverse narrow width effect and how it is taken into consideration in an inverter design. Now, we will discuss how inverse narrow width effect and mechanical stress are considered in inverter and NAND gate standard cell design. So, as we have discussed, 2 input NAND gate or 2 input NOR gate is of interest in low voltage or near threshold voltage design, because series stack of transistors having more than 2 transistors would not be good for near threshold voltage circuit design from speed considerations. In the NAND gate effective current model derivation, we had seen that it is the lower transistor switching which would be larger in the NAND gate. For upper transistor and lower transistor switching cases, the lower transistor switching would be larger. This is the layout of a NAND gate, 2 input NAND gate with single figure. So, this is what we will first discuss. So, we will consider lower transistor switching right now because that has a larger. So, we will first choose a certain value of Wn, which is the maximum finger width in that standard cell library. So, we will choose this that value of Wn. Okay, and Wn for both the devices for a systematic, for a simpler layout, the Wn of both the devices would be equal. Wp also of both the devices would be equal. So, we will change the value of Wp such that the effective currents are equal. Suppose the effective current of P MOSFET needs to be increased, we will increase the value of Wp. That is what we mean to say by. So, while calculating these effective currents, for example, for effective current of the P MOSFET, we will keep one of the inputs to be off, that is input is VDD, the other input switches from VDD to 0. And now the effective current of pull up, that is when input is switching from VDD to 0, is similar to that of the inverter. So, the effective current of the P MOSFET while charging is same as that of the inverter. So, that is why for pull up case, it is the effective current would be similar to that of the inverter for the case of pull up. Okay. And that would but for the lower transistor switching, that is for input going from 0 to VDD, then the effective current would be similar to that we have discussed for the lower transistor switching of NAND gate in one of the previous lectures. So, equate the effective current of pull up as we do it for the inverters with the effective current of the pull down for lower transistor switching. Okay. These two we equate. So, this is for lower transistor switching and this is that of the inverter. So, once we have done this, once the effective currents are equal, the Wp has been chosen. Now, we compute the leakage currents. So, what is this leakage current for P MOSFET? It is similar to that of inverter. What is the leakage current for N MOSFET? Now, we are dealing with the lower transistor switching. So, here the leakage current is flowing through the upper transistor, and what is the value of the intermediate node voltage? This is the node X. Okay. So, what is the value of this intermediate node voltage X? This is out, node out, this is VDD and VSS. VDD, ground, node X, node out. So, what is the value of the intermediate node voltage when both the leakage consideration? So, for leakage, both the inputs A and B, leakage through the N MOSFET, both the inputs A and B are at 0. So, in that case, we had said that Vx would be at Vx naught and we had calculated the value of Vx naught in the previous lectures. So, what is the value of the transistor A, which is upper transistor? This is the upper transistor A, this is lower transistor B. What is the value of VGS of the upper transistor A? It is VDD high. VDD high is the highest value the input would reach or node A would reach, that highest value VDD high minus Vx naught. This is the VGS of A, and VDS of A is similarly VDD, which is the output voltage, minus Vx naught again. And what is the source to body voltage of A? There is a negative body bias, it is again Vx naught. So, these are the voltages for which we calculate the leakage current of the N MOSFET. So, now this is the leakage current of the N MOSFET. Okay. So, we know the leakage current of P MOSFET and leakage current of N MOSFET. This is for both the inputs being VDD, and this is when both the inputs are 0, and we are considering a single input to be switching. So, input to be suppose we are considering input B to be switching. So, input A is VDD and input B would be switching like that. Okay. Calculate for these leakage currents for calculate VDD high. How you calculate VDD high? Similar to inverter. That is, you would consider the both the inputs to be 0. So, NMOS would have this IN flowing through them, and half of IN would flow through both the PMOS FETs. So, as in the inverter, we calculate the value of V out, which would lead to half of IN to be flowing through each of the parallel PMOS FET devices. So, that would give us the value of V out VDD high, which is VDD high. Likewise, we calculate VDD low for both the inputs being VDD, VSS low. So, that is the 0 value you would see in the static case. Okay. Input is held at a certain value for a long time. Now, compute the leakage current. So, leakage power, how would you compute? You know both these values, and VDD into average of these two currents would give you the average leakage power consumption. And then, because this is an inverter, this is an AND gate, we are taking FO3 load to be the typical load, not FO4 load. And for FO3 load of the NAND gate, then you calculate the FO3 delay using effective current. And that effective current of for pull up case is having a same formula which is same as that of the inverter. For pull down case, it is the lower transistor switching, the effective current associated with lower transistor switching in a NAND gate. Once you have calculated the FO3 delay, that gives us an idea of the delay of the NAND gate. Now, you calculate the energy again. So, dynamic energy is, because this is the input which is switching, input B. So, input B is input capacitance and VDD square. Leakage energy is again logic depth, because that many stages are there. So, multiply with the logic depth, and inverter FO4 delay. Why inverter FO4 delay? Because this is representative of the clock period. This is for the clock period, proportional to the clock period, that is what we would assume. And then NAND gate leakage power. So, NAND gate leakage power we get from here as we had calculated. So, see that this total energy is smaller than the specified value for per stage energy as we had calculated. So, path's total energy per cycle, if it is given, divided by logic depth, should be larger than the total energy that we get. If it is larger, then this single finger device design, single finger NAND gate layout is fine. Now, let us see how will we do fingering and increase the better the performance of the device of the NAND gate. Let us look at the layout. So, this is a 2-finger layout. This is input B, this is input A. So, this is also A, this is also B, this is out or Y. Okay. So, this is out, okay, and this is out. And where is node X? This is node X. Okay. So, and this is also node X. So, this is a 2-finger layout, or we can write it as NF equal to 2. We would now for the given for the WP that you have chosen for the single finger layout, you will increase the number of fingers to 2, and then 3, and progressively you will keep on increasing till your energy considerations are met. So, you will once you have increased it, if the effective currents do not match, suppose the so then you change the value. Suppose the effective current of P MOSFET is higher. Now, you want to increase the threshold voltage of P MOSFET. So, you will increase the value of WP. You will increase it till the effective current of P MOSFET equals that of the N MOSFET, like you did in the inverter's case. And now, for each finger, you will calculate the leakage current as we have done in the single finger case. For the chosen values of these finger widths, now you would again verify whether the VDD high and VSS low are within the limits that are set by the specifications, and then you will compute the leakage currents as we did for the single finger case, and compute the average leakage power by just taking the average of the input 0 and input 1 leakage powers, and then you would compute the FO3 delay to estimate the delay of the fingered NAND gate, and then you would compute the energies. Here you will again multiply with number of fingers, because that is the total energy of the you have done everything for a single finger, isn't all the calculations. So you will multiply with NF and compute the total dynamic and total energy. So which is total energy, which is dynamic energy plus leakage energy. Now if this is suppose smaller than energy from the maximum total energy that is allowed per cycle, so then increase NF. You increase NF and again check for the new NF whether the total energy is again smaller than maximum value of total energy that is allowed. Till that this condition is satisfied, you keep on reducing the number of increasing the number of fingers. So that would increase the speed, because threshold voltages are reduced, effective current increases. Then there is another important systematic variation, which is again layout dependent, like the inverse narrow width effect. So this is again one of the layout dependent effects. So here in the technologies, planar technologies and also all the technologies, FinFET or FDSY, you use stress layers, and so one of the stress layers is deposited above the gate. So this would either give a compressive stress or a compressive stress or a tensile stress, depending on whether it is a P MOSFET or an N MOSFET. So with different kinds of stresses, the mobilities of the electrons or holes increase. So accordingly the stresses are applied. So this mechanical stress is applied. For example, using a stress layer of this kind, one can apply a compressive stress or a tensile stress, depending on what is needed. Likewise, for P MOSFETs, instead of using silicon source and drain, you would etch out the silicon and deposit. So silicon germanium in general. So that would increase the compressive stress of the channel, increasing the in the x direction. Compressive stress of the channel, that would increase the whole mobility. So because of the STI is deposited at a high temperature, then it cools down, that again applies a compressive stress in the channel. So now when you increase the number of fingers, as you can see, the stress on the middle finger, the middle channel, and on the stress on the side channels would be different. So x direction stress because of this SIG would be maximum on the middle finger, because that is surrounded by several of these SIG layers. Okay. Likewise, this stress because of this compressive layer would also be different on the middle channel, because the compressive stress of these fingers is also applying on the middle channel. So on the middle channel the stress would be different, on the side channels the stress would be different. STI stress would be maximum on the side channel. So on the channels which are closest to the SC. So in a fingered layout, you would see that the stress is different on different fingers, mechanical stress. The x component, SXX, SYY or SZZ, the component looking into the screen. So when these are different, you would find that the mobilities of the carriers would be different. Threshold voltage would also change a little, but the mobility is affected in a major way. So the mobilities would be different for the carriers in different channels. So when you increase the number of fingers by a certain integral value, you would assume that the current would proportionally increase, but that would not happen because the mechanical stress would be different in all the channels. So in this paper we found that the mechanical stress can be empirically given by this, the x component for number of fingers being changing, so for being 1 is having a mechanical stress of x component this much, then this is the say number of fingers of some other value, say 4, the x component would change in this manner non-linearly, and these two are empirical parameters that we can extract for a given PDK. Okay. And Z component would also behave in the same way. SXX and SZZ both would behave in the same way. SYY would behave in a different way. So, here the mechanical stress would increase like the X component till a certain width of the finger. Beyond that, it would increase linearly like this. It would be a constant. So, but we would mostly be dealing with this for SYY also, because we are dealing with cases where the finger widths are not very large. So, say a standard cell scenario, the finger widths are not very large. So, therefore, for us this is important. So, this is the formula for relative stress relative to single finger case for all the three components SXX, SYY and SZZ for us. So, when you increase the number of fingers, you know how the mechanical stress changes for a given PDK. So, how would we estimate the changed value of mechanical stress and thereby the changed value of effective currents, and how to then modify the layout of the given gate, say an inverter or a NAND gate. So, first extract the values of P1, P2 and K for a given PDK by changing the number of fingers. So, you change the number of fingers and find out the change in current. So, change in current is mostly because of change in nominal current is mostly because of change in mobility. So, what would you do? You would change the number of fingers, and that would give us a value of how these three change. Now, all of them depend on the same formula. So, you can find out P1 and P2, and based on that you get an empirical relationship, this relationship, and the change in current is mostly because of change in mobility. So, you get how the mobility or current changes, that would give us and mobility is a multiplicand to the effective current. So, therefore, you get how the effective current changes with the number of fingers, and that would now change effective current of P and effective current of N device for a given number of fingers. So, change the P device width or finger width of the P devices, so that the effective currents match, and thereby the gate is now optimized for process induced mechanical stress also, gate layout, be it an inverter or a NAND gate. So, in this lecture we have discussed the NAND gate layout design considering inverse narrow width effect, and then considering mechanical stress, process induced mechanical stress, how we can do a final modification of the layout for an inverter or a NAND gate. So, we have discussed this. So, systematic variations, how can they be considered in standard cell or custom layout design scenario at the combinational gate level. This is the topic that we have discussed in this lecture. Thank you.